So previously we looked at some Apple interfaces and how we could segregate them. This time we're going to take a look at an interface that we've developed and segregate it ourselves. So here we have a media protocol. It's got quite a few methods and variables on it, and we want to reduce that. We want to segregate its interface into multiple smaller ones. There's a few implementations of it, and the key thing to notice is that we have some unimplemented methods, for example download or seek in this one, and that gives us an indication that this protocol is too big and should be split down into multiple separate ones. And comparing the functions and the implementations, it should be quite obvious where to split the protocols. And we're going to split out first a downloadable protocol and secondly a seekable protocol. So we start with the downloadable protocol, which simply has a function to download. We use an extension function for the can download functionality, which means we can remove this. And we remove download from the media protocol. And as streaming media is not downloadable, we remove its unimplemented parts. Purchase media is downloadable, so we add the protocol to it, but keep the method of download there. TVR media is not downloadable, so again we remove its unimplemented parts. So if we head back up to our media protocol, it's now a bit smaller, which is good. We can also extract out a seekable protocol using much the same mechanism. Now we'll pull the function from media. We'll make a protocol extension again. So streaming media is seekable. So again, we add it. Purchase media is also seekable, so we can add that functionality in the protocol. TVR media is not seekable, so now we remove this and we remove that. And now you can see that our media protocol is a lot smaller once we remove the can seek method as well. So you can see the protocol is much smaller and tighter, and we still have all the safety of the can download and can seek checks. So any users of media still has pretty much the same API. They just have to cast the additional protocol. And we have a good thing, which is we avoid all the runtime crashes, which is the fatal errors that you saw implemented. So now there's no way we can mistakenly crash the app. So this is a good example of using protocols ending in able, such as downloadable and seekable, to find out roles within a protocol that could be split out into further subprotocols. This last part takes a look at dependency inversion, together with all the other parts of Solid, and how they not only make for cleaner code, but also make code significantly easier to test. Unit testing code is an important part of building production-ready apps. Code that can't be unit tested is easier to break, or, at least, makes it harder to understand when and how you've broken it. Solid code is almost always easier to test than non-solid code, because it's architected better. Dependency inversion in particular helps us set up tests easier and makes them less brittle. We're going to use the cute pets loader from the end of part 1, which, if you remember, focuses on dependency inversion and also uses some of Liskos substitution. This is the cute pets loader, and if we were to test this, given it uses dependency inversion, it would actually be pretty easy. Let's take the example that if data is loaded correctly, it's displayed on the pets view. In that case, all we have to do is make a fake network that returns us some data and a fake view that we can assert against. and that's actually going to be quite easy. So here's the test implementation of our test network, and we're setting it up so that it always returns a success. We're not going to worry about the show error and hide error methods for now. So this test is concise and simple. It tests the logic of the Qt loader and nothing more. And it works. Let's take a look at a non-solid version of the Qt loader, where we're not using dependency inversion or Liskov substitution. Here the test would be much harder to implement, and right now it would actually be impossible. The reason is we would have to make some special way of accessing this URL session, because we'd have to override it in the tests. We'd have to override the data task to return us something we can test against. And we'd have to create a UI label and assert against that, which is a bit odd. And that's a lot of effort for such a simple test. Additionally, if we were to decide to use another networking library instead of URL session, we'd not only have to rewrite a lot of the logic here, as we saw in part 1, but also we'd have to rewrite a lot of the logic of all of that test we'd have to set up as well. This is sometimes called pouring concrete on your code. And what I mean by that is your test is so tightly bound to the production code, it's impossible to change just one of them. So dependency inversion allows easy unit tests by itself, but coupled with the rest of Solid, it can make your life as a developer much easier. By ensuring the Qt loader has only one responsibility, we focus the unit test. By making sure it's open to extensibility, we can swap our pets view and network out when we need to. By removing implementation detail from the network API, we make it quicker to generate our test version. By making the network protocol small, unlike URL session, we reduce the effort needed in the test, and we reduce the amount of things the Qt loader really needs. And finally, by inverting our dependencies, we don't have to make any test-specific changes to our production code. And that's the end of the course. I hope this helps you get started with Solid principles. Interestingly, they're far from new, and they were first written around 20 years ago, but they've stood the test of time. They'll make your code easier to work with, both for you and your team.